Alright, we're going to begin section 15.5 in this video, which is surface integrals. Alright, so in this section, we will learn how to integrate over a surface S and your textbook is going to tend to use sigma for the surface, but I'm just going to use S for simplicity. The surface S in space, so versus a surface being in the XY plane. So now we have some surface in space. Now what the approach we're going to use will work in the XY plane, of course, but more generally we're going to be looking at doing things in 3 dimensions. So now the region over which we integrate will just be some surface, whatever you can sketch, whatever surface you want to sketch. And we'll put these little lines on it to indicate that this is an actual surface, not just a curve. So this is our surface S. So when we say a surface, we're not talking about a 3-dimensional solid. We're talking about a surface that has like a negligible, thickness to it. So we're not talking about like when we did triple integrals over a 3-dimensional solid, and nor are we talking about line integrals over a curve. At the moment, we'll go back to that because there's a boundary curve on the surface. We're just strictly talking about integrating over the surface. Now in 15.5, we'll talk about integrating a scalar function over this surface, and then in 15.6 we'll talk about integrating a vector function over this surface, just like we did with line integrals. So try to always keep in mind, am I integrating a vector function or am I integrating a scalar function? All right, so there S is the region over which we will integrate. All right, so any function f of x, y, z defined on S would be in 4 dimensions. Thus, we would not be able to represent it with a sketch nonetheless. There are reasonable functions we may want to integrate over S. We may want to integrate over S such as T of x, y, z, the temperature at any point x, y, z on S. The temperature at any point x, y, z on S. So now we'll look at the formula as to how we actually go about evaluating a surface integral of a scalar function. Let S be a smooth surface given by R of uv equals the vector whose first component is x of uv, second component is y of uv, and third component is z of uv. Where uv are points in the domain D. If f is continuous on S, then the surface integral of f over S is, all right, we're going to look at what that is, but one thing I want to make sure I point out is that we've learned in section 14.9 how to parametrize surfaces. That's not going to go away. Just like we saw our ability to parametrize curves pop up again when we started chapter 15. Now we're going to have to rely upon our ability to parametrize surfaces again. So when you encounter a surface integral, you may not necessarily be given a parameterization like this. So you might have to parametrize your surface yourself. And also remember, this set D is just going to be some underlying set. We won't see this in our picture of S. It is just the parameter space for U and V. So when we were doing when we would parameterize a curve, for instance, we would have our parameter T was usually we would say T is between A and B. Here we say the points U, V are in this set D, and then we would have some bounds, say U, whatever varies between 1 and 3, and V might vary between whatever 0 and U plus 7, because remember we're going to end up setting up, when we look at this, our bounds for U and V can be any simple region in this set D, or simple region in R2, excuse me. All right, so now, or sorry, 2 dimensions, not R2. They're the same thing, but I just try not to use that R2 terminology. So let's go to the next page. All right, so now the notation for the surface integral we'll use is the surface integral over S. So it just looks like a double integral notation of f of x, y, z, which we can see is a scalar function there, and then d capital S. So this is just with respect to surface area is what that stands for. Now, how do we actually go about evaluating that? So this ends up being the double integral over the region D, where u and v vary on that region D. We take f and we put in our parameterization of the surface. So f of x of uv, comma, y of uv, comma, z of uv. And then we multiply that by the magnitude of the cross product of, so by the magnitude of r sub u cross r sub v dA. So in order to evaluate this surface integral, it boils down to us just evaluating a double integral. Now, shorthand notation for this, the same thing is the double integral over d of f of r of uv, just saying we take our parameterization for the surface, put it into our function, and then multiply by this thing. So times the magnitude of r sub u cross r sub v dA. And notice in here, everything will be in terms of u and v. So you'll have sketched your region D, whatever the region is. Because we're doing a double integral, you'll sketch the region D. Not your surface S, you don't need to sketch your surface, but you will sketch the region D for your parameters, u and v, and look and see whatever. It's a polar region, you know how to set this up as a polar integral. If it's a rectangle, like a type 1 or type 2 region, you all know how to do those things as well. All right, so we'll stop this video here, and then the next video I will do some examples from section 15.5.